All right, so picking up here with chapter 14. So in this chapter, we're going to talk about liquids and solids, maybe more liquids than solids. We're going to talk about some important things in this chapter. We're going to talk about phase changes. We're going to talk a little bit about water, and we'll talk about some important sort of interactions that occur with molecules, which are known as intermolecular forces, which really determine a lot of substances, things like their boiling points, melting points, are affected by how they interact with one another. So we're going to start with here water, and a little bit about water. So water obviously is colorless, tasteless sort of substance. 1 atmosphere is the standard sort of pressure that we usually think about things. And at 1 atmosphere, the normal sort of melting point and really freezing point of water is 0 degrees Celsius. Remember that both melting point and freezing point basically occur at the same temperature, which in the case of water is 0 degrees Celsius. At normal sort of pressures as well, water will start to boil at 100 degrees Celsius. And at the normal boiling points where we have obviously our transition from liquid to gas. And we have basically liquid water between 0 and 100 degrees Celsius. One sort of interesting sort of property of water that's a little different than a lot of other substances is its density. Water, normal sort of density, or the density really of liquid water, which is really what this one is here, is 1 gram per milliliter. Density does change with temperature, but for most problems, most situations that you come across, if you ever sort of need the density of liquid water, usually most people will use the 1 gram per milliliter unless otherwise sort of specified, but you should keep in mind it does really change with temperature. One unusual property of water, as I mentioned, is actually the density of it. Most substances in their solid form are much more dense than in their liquid form. And for water, that is kind of the opposite. When we have really water in its solid form, which is ice, as we know, when we put ice in our drink, right, it kind of floats to the top. And actually, ice is less dense than liquid water. And it has a lot to do with how water molecules basically interact with other water molecules. So when something like water, which is polar, which means, again, the oxygen side is more negative than the hydrogen side here of water. When a bunch of water molecules sort of get together, what ends up happening, especially when they start losing energy and coming into that sort of solid state, is as they sort of interact with one another, it creates these large sort of open areas in between the different water molecules. And because of that, if you remember sort of what we talked about when we talked about density way back when, density is mass divided by volume. That means that when ice sort of freezes with all this sort of open space between the water molecules, they can't really get really tight to one another. We're really increasing the volume there in that the equation. And when we have a larger number on the bottom there, the density will actually come down. So water actually is, again, more dense in the liquid state than in the sort of solid state. Also really important for like when water freezes, right, in lakes and stuff like that, right? Water freezes from the top down, right? Not from the bottom up, which is good for fishes and stuff that live in the water, because if it did the other way, everybody. But basically what happens is, because when it starts to freeze, the heavier water, like the 4 degrees Celsius water, actually goes to the bottom. The lighter ice actually floats to the top because it's less dense, and creates this sort of insulated layer up there on top of the water there that freezes, and it's still liquid water underneath, right? You see all those videos of people that walk on the frozen lake and then fall through right into the freezing water that's underneath, because the top layer is frozen, because the lighter, more lighter dense ice goes to the top and freezes, but still the warmer liquid water is still there on the bottom. We'll get back to that in just a second. So let's talk a little bit, though, about what happens as we kind of change states and as we go from one state to the next. I think we talked about it early on in the semester, but we do obviously have our different states, solid to liquid, and that's the process of melting. We could go back from liquid to solid, which is the process of freezing. We could go from liquid to gas, which is the process of evaporation. We could go from gas back to liquid, which is the process of condensation. We could go from solid directly to gas, skipping the whole liquid stopover, and that is what is known as sublimation. We could go from gas also all the way back to solid, also skipping the stopover there in liquid, and that is deposition. So those are our sort of 3 states of matter. Those are our really 6 sort of transitions that occur. And we talked about it earlier on as well, but we will sort of talk more about it here as we go through it. There's energy associated with as we go from, say, solid to liquid to gas. As we go from those processes, those are all endothermic processes, which means heat and energy has to be absorbed. Like you take the ice cube, picks up energy, starts to melt. You boil liquid water, you get steam. So those are all processes where we need to absorb energy, which again is our endothermic process. And the opposite is true, obviously, as we go from gas to liquid to solid. We have to actually release a lot of energy. So we have these gas molecules that are flying around. As they lose energy, they can no longer fly around as fast, which means when they collide with other gas molecules, they kind of stick together and kind of fall into the liquid phase. If you continue to remove the energy, you will get it to the solid phase. And these are all processes where energy is released, which means, again, they are exothermic processes. So what affects how much energy is maybe required to do some of these transitions, and also what affects things like boiling, melting points, freezing points, are how intermolecules basically interact with themselves. There's 2 types of forces that we'll talk about, and we'll talk a little bit more in a little bit later on some of these. But the first type of force is what's known as an intramolecular force. And an intramolecular force is really the force that holds like an individual molecule together. So for example, if we did take our water example here, within water, there's basically 2 bonds. There's a bond between oxygen and hydrogen on one side, and another covalent bond between oxygen and hydrogen on the other side. And that's an intramolecular force within the actual molecule itself. So covalent bonding, when we're sharing electrons like we do between the oxygen and the hydrogen, is intramolecular force. For ionic compounds, the electrostatic attraction, the charge and attraction between the positive ion and the negative ion, are also intramolecular forces. And those are different than intermolecular forces. Intermolecular forces are the forces that hold one entire molecule together with another molecule. And that could be one molecule with another one that's the same, or another molecule and a different type of molecule. So if we did take, again, a couple of water molecules here, and as I mentioned earlier, oxygen being more negative, hydrogen being more positive, when it gets together, for example, with another water molecule, it is the positive side of one water molecule that's attracted to the negative side of another. And pretty much there are some different types of intermolecular forces that we'll talk about in a little bit more detail later on. But the basic interaction in all intermolecular forces is pretty much that interaction. It is the positive side of one molecule is attracted to the negative side of another. So all sort of intermolecular forces boils down to pretty much opposites attract, and positive side of one attracted to the negative side of another. And again, that is what's going to hold those molecules together. So it can, again, as I mentioned, be pretty much just water molecules with other water molecules, or it could be, say, water molecules with something else, or any other two types of molecules could come together, are the intermolecular forces. Intermolecular forces are typically always not as strong as intramolecular forces. So the forces that hold individual molecules together are always much stronger than any type of intermolecular force that you could have. And we know that by a simple sort of example that we've all done, which is we've heated water before, right? And you got water that starts to boil. And when you go to heat water and it starts to boil, the first bond that really breaks is the bond there between basically the two water molecules. And what happens is that intermolecular force is broken, and that allows this water molecule to go off into the gas phase, allows this guy to separate off and go into the gas phase. And we get those individual water molecules that basically have freed themselves up from one another. And that is because the intermolecular force is much weaker than the intramolecular force. If it was opposite and the intramolecular force was actually a lot weaker than the intermolecular force, what would happen when we would heat up water is we would get alphabet soup. We would start breaking the individual bonds and everything, and we would generate hydrogen gas and oxygen gas, which is not a great thing to generate if you got fire there. So we know just by our experience that that doesn't happen. And again, the intermolecular forces are always much weaker than the intramolecular forces. Any questions on that there? They are also, as we'll talk about, responsible for boiling points, melting points, and freezing points in terms of their temperatures. The stronger the intermolecular force, we typically will see a higher boiling point and freezing point because it takes more energy to separate those out. So the stronger that connection between molecule and molecule, more energy you have to put in there to try to get them apart. And the more energy you have to put in there to get them apart means the higher temperature at which they will boil. The weaker the intermolecular force that holds molecules together, the much lower boiling points and melting points that we see, because it doesn't take a lot of energy to get them to break apart from one another, is a much lower sort of temperature. So when we actually do change phases, so for example, if we go from solid to liquid, or liquid back to solid, and liquid to gas, or gas back to liquid, there is a certain amount of energy required to simply do that transition. Not change the temperature of the substance, but take a substance at its normal melting point or freezing point, or its normal boiling point, and change the phase. So for example, if we look at going from solid to liquid, or backwards here, liquid to solid, the amount of energy required to do that, and for water here, is 6.02 kilojoules per mole. That is what is known as the molar heat of fusion, or sometimes abbreviated as the delta H of fusion. Remember, delta H is the enthalpy, and that is the heat of fusion. And that is simply the energy that's required to pretty much take a substance like water and take it from 0 degrees Celsius ice to 0 degrees Celsius liquid water. Not change the temperature, but just solely do the transition from one phase to the next. And that is the heat of fusion that's required to do that. By the way, this conversion converts out to roughly 333 joules per gram to do that. There's also a certain amount of energy that's required to do this transition that happens at the boiling point to take a substance from liquid to gas and backwards. And that is known as the heat of vaporization, also sometimes referred to as the delta H of vaporization. And that for water, for example, is 40.6 kilojoules per mole, which is roughly 2260 joules per gram. So we see a couple of things here. It takes more energy to do what transition? Solid to liquid or liquid to gas? takes a lot more energy to do the liquid to gas transition because it's about 2200 versus 300, therefore solid to liquid. That's because as you go from solid to liquid in the solid state, everybody's pretty much together. In the liquid state, everybody's still pretty much together, a little bit more room for movement. As you do the transition from liquid to gas, pretty much everybody needs to break apart into gas molecules, which means they're flying around away from one another. Takes a lot more energy to get everybody away from each other. So the transition of going from liquid to gas is always a lot more energy required than going from solid to liquid. Any questions on that there? The other really important thing here that we were talking about, which is the idea of energy, is we have certain values when we calculate energy value that tell us whether or not something is exothermic or endothermic. If you remember, if it is a endothermic type calculation, usually the energy value will end up being a positive number. And if it is an exothermic type of situation, the energy value will usually be a negative. That means when we use something like the heat of fusion or the heat of vaporization, it doesn't matter which way you're going, the number will be the same, but the sign will be different. So if we were doing the transition of solid to liquid, that's an endothermic process. It would take positive 333 joules per gram to do that. If we were going the other way, liquid to solid, we have to remove that much energy, and it would be represented as minus 333 joules per gram. Again, the number is the same, just the sign is different there. And the same thing for our heat of vaporization. If we were going from liquid to gas, that is going to be a positive 2260. And if we were going from gas back to liquid, be a negative 2260 joules per gram. So we could do these sort of calculations, and remember that always when you are sort of quoting or calculating some type of energy sort of value, the sign is really important. If it is negative, you should usually keep the negative value for your energy sign, because again, it indicates that it's an exothermic process. And obviously, if it's a positive one, it should stay positive, as it indicates that it is an endothermic type process. Any questions on that there? So let's take a look at sort of water and this curve we skipped there. There it is. So this is a heating and cooling curve for water. And obviously, as you go from ice, which is really our solid here, to basically liquid water in the middle, to steam, which is really the gas phase. As you go from solid to liquid to gas, that's a heating curve, which means it's an endothermic process. Energy has to be put in along that journey. And obviously, as you go the opposite way, if you started in the gas, heading down to the liquid to the solid, that is a cooling curve. Energy has to be released, exothermic in that process. So we see our transitions here. And what we see here is at 0 degrees right there, it is a flat line. And that is the normal melting point and freezing point for water. And because this line is flat, that means the temperature is not changing. And if we wanted to sort of calculate the energy required to go from solid to liquid in this case, right there is where our delta H of fusion or heat of fusion would come into play. Remember that it is not until you get a little bit below 0 degrees Celsius that you really do have ice. And it's not until you're a little bit above 0 degrees Celsius that you really have liquid water. Exactly at 0 degrees Celsius, you have both phases in equilibrium with each other. You basically have like ice crystals. So you got a little bit of solid ice, got a little bit of liquid water happening. You got both phases basically happening at the same time. The same thing sort of happens here. If we come up here, this is 100 degrees Celsius here, which is our normal boiling point here for water. And that is where we have our transition of going from liquid to gas, vice versa, backwards. And the same deal here is not until you get a little bit above that 100 degrees that you have gas, not until you get a little bit below the 100 degrees that you have liquid water. And you have, again, both phases sort of happening at the same time. It is essentially what always happens at the surface of any liquid. You have guys jumping out of the liquid phase into the gas. gas molecules dropping back into the liquid. And it just continuously sort of happens always in a liquid. It also is a flat line, which means we're not changing the temperature. It happens exactly at 100 degrees. And that is where we would use our delta H of vaporization in that situation to calculate how much energy is required to do that change. Now, the other part of these curves here, we've actually dealt with, although we may not know that, but we have dealt with it earlier. If we go from, say, 0 degrees Celsius to 100 degrees Celsius, all through this green line, that is all liquid water at that point. And that means that the phase of that substance stays the same through that whole transition, but we are changing the temperature. So when we have a situation where we have a substance where it is in the same phase, but the temperature changed, we could calculate the energy by using an equation we've used before. That is the specific heat equation. If you remember, that is our Q is equal to ms delta T that we saw in, I don't remember, chapter 10 maybe or something like that way back when. Remember, Q here is energy or heat, and that is joules or calories is typically the units. M is mass, which is usually grams. S is the specific heat capacity, which is joules per gram per degree Celsius, or calories per gram per degree Celsius. And remember, as we talked about when we were talking about this, the delta T should always be the final minus the initial, and that usually is in degrees Celsius in the case of this one equation. Probably the only equation in chemistry where we do not convert the temperature to something else. And the important part of the change in temperature, as we talked about, is you always want to do final minus initial, because that is the one that determines whether or not you get a negative number or not, right? So if somebody absorbs energy, their final temperature will be larger than their initial, so it will be a positive number. And if somebody releases energy, right, their final temperature will be less than what they started with, and that would give you a negative number. And that's really important that you do that. Couple other numbers is important, right, is like the specific heat of liquid water. That's a number that we've seen, 4.184 number, joules per gram per degree Celsius, are 1 calorie per gram per degree Celsius. And that is the conversion between a joule and a calorie. And 1 calorie, there is 4.184 joules, right? So those are some conversions from the back. So really anywhere on this graph where you have a substance that's basically the exact same thing, but all you did is change the temperature, you could use the specific heat equation basically to calculate how much energy is happening there. Anywhere where you transition that the temperature stays the same, but the phase changes, it should be some type of heat of fusion, heat of vaporization type calculation. So on this graph, again, some other places where we would use the specific heat equation. Here, obviously, that's all gas, and here, down here, that is all, say, solid. It's important as well in this equation that you do use the correct. So, for example, if I was doing something where I was changing the temperature of gas here from, say, 112 degrees to like 110 degrees, because that is gas, I would use my specific heat equation, but the specific heat of water in the gas phase is like 2.03, or actually 2 joules per gram per degree Celsius. So it is a different specific heat capacity than liquid water. So you want to make sure that you look it up and get the right value. Just like down here in ice, it's like specific heat capacity of water in the solid phase is like 2 as well, joules per gram per degree Celsius. So the specific heat capacity does change depending on what phase you're in. Water is a common example that you want to be careful of and make sure that you do grab the right one. Any questions on that there? So how do we tie all these things together? So let's just say we did an example where, go back this way maybe, there we go. Let's say we want to know how much energy is required to change 110 grams of ice at -3 degrees Celsius to steam at 100 degrees Celsius. So when we do these transitions, there's actually several steps that occur along this process. So if we, maybe I'll just steal this graph here and erase this stuff. If we look at this sort of curve here, the very first thing that we would be doing in this process is we're starting at -3 degrees Celsius. We actually have to take it from -3 degrees Celsius basically to 0 degrees Celsius. So the first step that we would do in this calculation is to take it from -3 degrees Celsius to 0 degrees Celsius. So the first step, -3 degrees Celsius ice to 0 degrees Celsius ice. That is a substance that's in the same phase. It's ice all the way through, but we're changing the temperature. So here we would use our specific heat equation to calculate that. So using that, our Q would be our 110 grams of ice. In this case, because we're at ice, we do not want to use the 4.184 number because that's for liquid water. We would want to use the number that's for ice, and I think it is 2.03 joules per gram per degree Celsius. Once again, that is the specific heat capacity for ice and not liquid water. Once again, here we're going to do our final temperature, which in this case is 0, minus our initial, which is -3. And that is going to give us here, in this case, 110 times 2.03 times basically 3 in this case will get us 669.9 joules in this case. So that energy that we just calculated here is the amount of energy that's required to simply take our ice that started at -3 degrees up to 0 degrees Celsius. And at this point, it is still ice. In order to get it to steam, we then would have to take the ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So we have to do a phase change at this point. And if we keep track of it there on our map, we're basically sitting right here. The next thing we would have to do is that phase change to take it to 0 degrees Celsius liquid water from ice. And as we talked about a second ago, that is our heat of fusion that allows us to do that. That's the energy just to simply change the phase, not the temperature, but to change the phase of a substance from solid to liquid. So the second step that we would have to do in this process to get us all the way up there to steam is we would have to take our 0 degrees, let's try that again, 0 degrees Celsius ice to 0 degrees Celsius liquid water. And once again, that is the delta H of fusion that allows us to do that. I'm going to use the joule number, which is for water, 333 joules per gram is the heat of fusion for liquid water or for water. If you were doing some other substance, you would obviously use a different number depending on what their heat of fusion is. So we'll take our 110 grams of ice at this point. We will use that as a conversion factor. We're going to take our 333 joules per gram. Grams are going to cancel. And this is an endothermic process, which means that's going to be a positive number. So 110 times 333. Going to get us about 36630 joules. So that energy value right there represents the amount of energy that's required to do that phase change. Take it from 0 degrees ice to 0 degrees liquid water. So we've now done a phase change and we're sitting now in liquid in terms of our phase. In order to get to steam, we have to really go through the entire liquid scheme there of temperatures. So if we were to look at our map, our graph here, we're now sitting here, 0 degrees Celsius of liquid water. We need to go through this entire run to get to the normal boiling point here. which would be our next step. So we got to go through now for the third part of this calculation. 0 degrees liquid water to 100 degrees liquid water, which is the normal boiling point here of water. And that is a situation where it is all liquid all the way through, but we are changing the temperature. So once again, we would come back to our specific heat equation, which is Q is equal to ms delta T. Putting in our number here, 110 grams. Now that we are at liquid water, we could use our normal 4.184 version there of our specific heat capacity, because that is for liquid water. And once again here, we're going to do our final temperature, which is 100, minus our initial, which was 0 in this case. And now we will end up with 110 times 4.184 times 100. Looks like 46024. So that is the amount of energy we would have to supply to take really our liquid water from 0 degrees and get it all the way up to 100 degrees Celsius, which is the boiling point. Kind of like all that energy you need to do when you put a Bunsen burner under your water to get it to start to boil, basically, right? So that is basically what we're trying to do here. Take our liquid water, start to get it to boil, and get it to that boiling point. At this point, if we sort of look at our graph, we are now sitting at 100 degrees liquid water, which is pretty close to what we want, but we want 100 degrees of steam, which is gas. So we have one last phase change to occur, and that last phase change has to happen here. So right now we're sitting right there. We want to end up right here. So we have this last phase change that occurs right there. And that is going to be the delta H of vaporization. Is going to allow us to do that phase change and take it from 100 degrees liquid water to 100 degrees steam, which is what we want. So to do the last part of the calculation here, we're going to take our water that's now sitting at 100 degrees Celsius liquid water to 100 degrees Celsius steam. And that is going to be our heat of vaporization to do that. And for water, again, it's about 2,260 joules per gram. So we'll take our 110 grams of water, which we should not have lost any along the way, as long as we didn't spill anything. And we will take our 2,260 joules per gram. And we will end up, in this case, 110 times 2,260. Going to end up as 248600. And what we see here, that is the energy to do that final phase change of going from liquid to gas. And if we do compare it to the phase change to go from solid to liquid, we do see here it takes a lot more energy, right, to do that transition, about 7 times as much energy to do the transition of going from that liquid to the gas and getting everybody completely apart from one another so they could go into the gas phase, rather than going from solid to liquid where they're still relatively associated to each other. Any questions on that there? Now, if I wanted the total energy to do this entire run, what should I do with all these numbers? I just need to add up all those numbers. So if I wanted the total energy that's required to do that whole journey, I'll write it here. Total energy would be basically the energy of step 1 plus step 2 plus step 3 plus step 4. Basically add them all together, kind of like Hess's law that we did earlier on, where you could add all these different steps, right, and get the total amount of energy. And if we did that in this example, 669.9, which was our first step, 36,630 was our second step, 46024 was our third step, and 248600 was our last step. We end up with approximately 331923.9 joules. And if we want to convert it to kilojoules, which is commonly sometimes how these answers are given, we'll divide it by 1,000 to convert it into kilojoules. And we end up with 332 kilojoules of energy is required to ice cube at -3 degrees all the way up to basically steam at 100 degrees Celsius. Question on that. Now, if I didn't stop at 100 degrees Celsius, I went to like 105 degrees Celsius, I would have one more transition, which would be a specific heat equation because that's steam to steam. And you would do 105 minus 100 and do that last part if you want to go further. The other question is, what would be the difference if I started at 100 degrees Celsius steam and took it all the way down to -3 degrees for ice? The only difference in all these calculations is each of these numbers would end up being negative because it's exothermic. So this first step here, these guys would flip, which would give you a negative number. This guy here would be negative, going the other way. These guys would flip, which would give you a negative number. And this guy would also be negative if you were going the other way, which would give you basically the exact same numbers, except that they all would be exothermic and should end up as a negative value. Any questions on that there? All right, we'll lay it up there for today.